very nice to be back here in DC with good weather. Really, growing up as an American in the Mississippi River Delta region, depicted here on this map, it's a great honor to deliver this lecture in this fine American institution. And actually this is also my first Q-Crypt. Heard many great things about the conference over the years, that it's done a fantastic job of bringing together experimentalists and theorists working on quantum cryptography, so I'm very grateful to have this opportunity to participate. Okay, so I'm going to tell you today about some work that I did in collaboration with Marco Tom-Michel and Mario Berto. And it's in this paper that's here on the archive, WTB. Okay, so the setting that we're interested in is depicted in this diagram. And what we have is we're assuming we're given a description of a quantum channel. Okay? And this is my kind of abstract depiction of a QKD protocol that's using the channel little n times, so some finite number of times. And what we have are Alice and Bob are allowed between every channel use to use local operations and classical communication. So by that I mean they're allowed to use whatever quantum devices like. They can exchange as much classical communication as they'd like. What I have not depicted in the diagram is the eavesdropper, so I'll just tell you about the eavesdropper. The eavesdropper is allowed to hear all of the classical communication exchanged between Alice and Bob, allowed to receive a copy. So after an initial round of LOCC, Alice sends one of her systems into a channel, then an output emerges for Bob. Something I haven't depicted on the diagram as well, and it's coming from a theorem in quantum information theory called the Stein-Spring theorem. Every noisy channel can be considered as arising due to a unitary interaction with an environment. And the receiver gets one system that's output from the unitary, and in this model of quantum key distribution, we'll assume that the eavesdropper gets the full environment. That's like paranoid scenario. And then between every channel use, there's a round of LOCC. So this kind of thing repeats little n times. So LOCC, channel use, and then at the end, there's a final round of LOCC, and there's a key system for Alice and a key system for Bob. Okay? And so what we want at the end is that the state of these systems is classical, uniformly random, perfectly correlated, and in tensor product with the eavesdropper. That's the ideal key. I don't have a chalkboard, but Roger had it in his slides from his tutorial. Okay, and the thing that is, I think, of great practical interest is something that I'll call non-asymptotic private capacity. So typically we talk about capacity, which is an asymptotic statement, but for practical protocols, we're interested in non-asymptotic private capacity. So I'll just define this in words. And what I mean by it is the maximum rate of approximate secret key that Alice and Bob can achieve by using the channel little n times. And we might also be interested in energy constraints. There's an energy constraint on every input that Alice is sending into the channel. In practice, you might have some transmitter that's limited with some energy constraint. By approximate secret key, I mean that the actual key at the end of the protocol in fidelity is, it has fidelity larger than 1 minus epsilon with the ideal state that I described previously. That's what I mean by approximate secret key. And what I'm showing here is the quantity of most interest in this talk. So what is going on with this quantity? This is the rate of secret key that two parties can make by using the channel big N, and we're fixing parameters, little n, the number of channel uses, ns, signaling photon number, so the mean number of photons per channel use, and epsilon is the infidelity of the key. We want the ideal key to be a fidelity larger than 1 minus epsilon with the actual key. Okay, so you fix those parameters, and then we optimize the rate with respect to those parameters. This is the quantity of interest. Double arrows indicate forwards and backward classical communication is allowed between every channel use, an arbitrary amount that they'd like to do. And then if there's no photon number constraint, maybe we want to characterize this quantity independent of photon number, so that the resulting quantity is just a characteristic of the channel. We could take an optimization of the rate with respect to the energy use per channel use. Okay? So those are the quantities of interest. And the main practical question is how to characterize this. Ideally, we'd like to characterize it for all n, for all numbers of channel uses, for all energies and all epsilons. That might be a hard thing to do, but I'll mention, I'll discuss in this talk how to attack this question. And then we can have the same question for the quantity that's independent of energy. And the answers to this questions give what we could call the fundamental limitations of QKD. We can figure out lower bounds, we can figure out upper bounds, we can try to characterize this quantity in various ways, this non-asymptotic private capacity. Okay, so something that I had a previous work with Masahiro Takioka and Saikat Guha, and in this previous work we figured out some upper bounds on these quantities, and we advocated this as a method for establishing a benchmark for quantum repeaters. The idea being that, in this picture that I showed in this slide, there's no quantum repeater. There's just the channel connecting Alice to Bob, and there's local operations and classical communication. So if we figure out a bound on what can be achieved without a repeater, then if you're an experimentalist trying to build a quantum key distribution system, you can exceed this bound, exceed upper bounds, then you can claim that you've really built a quantum repeater. That was one of the main messages of that paper. And so in this talk, I'm going to get into trouble for writing this statement. I know I will, but I see this kind of language in many papers out there, so I'm just going to say it. We find the tightest known upper bound on these non-asymptotic private capacities, and thus we get the best known benchmark. I know that I'll get into trouble because a week from now, a month from now, a half a year from now, someone will prove a tighter bound than what I talk about today. Anyway, okay, so what was known before, let me just talk a little bit about that. And to do so, we have to leap back to QCrypt 2014, like this leaping sheep is doing to Paris. I don't know if you can see it, but the sheep is decorated with alphas and betas and psis and phis. We've had some very interesting logos over the years. And at that QCrypt, my colleague Masahiro presented the results of this paper. So I'll just review those briefly. Okay, so we're interested in bounds on non-asymptotic private capacity of quantum channels. And the one that appears to be of most practical interest is the photon loss channel. Okay, so what is that channel? There's a very simple model. Intuitively, you can just think of it as a beam splitter. So Alice can input light into one port. The environment can inject light into another port. But in this model, we're assuming that the environment is injecting the vacuum. There are other models I'll talk about later where the environment can inject thermal states. And the only thing that characterizes the channel is this transmissivity parameter. So this is characterizing the average fraction of photons that make it through from Alice to Bob. And what we assume is that the environment, everything that's lost along the way, the eavesdropper has. Okay? So that channel I'll denote by L for loss and eta for transmissivity. Okay, so the question that I mentioned previously to characterize bounds on non-asymptotic private capacity, it is a tough question. So let's consider limiting cases. And this is exactly what Shannon did many years ago when trying to characterize capacity. Thought, well, geez, this is really hard. Let's give ourselves a little wiggle room and take some limits. So that's what we did in this initial work that Masahiro presented. Okay, so a case of interest, and this is typically called the Shannon regime, is where the number of channel uses goes to infinity. Take that limit, and then as the infidelity of the key goes to 0. Okay? So what we found is an upper bound on this asymptotic private capacity, which is given by this difference of entropies of a bosonic thermal state. Here what you see are the channel transmissivity that depends on the channel, and the mean photon number allowed per channel use. That's some energy-dependent bound that we figured out. And it was based on the squash entanglement measure that was developed by Christenel and Winter. They showed that this quantity is an entanglement measure. Later on, Christenel showed that it's an upper bound on distillable keys. So we were very much appealing to some of the earlier work developing this bound. Okay. And then we might also be interested in a bound that depends only on the channel, where there's no energy constraint. So in that case, we found this upper bound. So it's just log of 1 plus eta over 1 minus eta. And essentially why this bound comes out from the energy-dependent bound is that this difference of entropies is a monotone increasing function with energy. Optimize it, it has a limit, and it's given by this quantity right here. Okay? And so what this work did was to establish the existence of a fundamental trade-off between rate and loss. This is something that maybe people considered to be obvious, that there would be a trade-off, but we provided a mathematical proof of this fact. And the thing about it is that it's finite for all eta between 0 and everything up until 1. If you plug in 1, you get infinity. But in that case, it's an ideal channel, so it has. If you have infinite energy, then you'll have infinite capacity for a noiseless channel. Okay. And the main drawback with this bound is that it's an asymptotic statement. Okay? And so as a consequence, it has limited applicability in practice, but it can still be viewed as some kind of guideline. The other thing, so I said this thing about having a mathematical proof, but a little bit later we discovered there's issue with, this is for the experts, this thing called shield systems having to do with private states. And there was some unaddressed issue with unbounded shield systems that's now fixed in a paper that I put out this summer. Realizing that, freaked out a little bit and then thought about it. Okay, so this is a plot from that paper that Masahiro talked about. And what we have is, on the vertical axis, secret key rate, and on the horizontal, channel loss measured in decibels. Because we learned that this is kind of the thing that engineers like. And you can translate the x-axis by to kilometers by just using parameters that are available for optical fibers that are out there. Okay, so up at top, this purple-pink line bound based on squash entanglement, and it shows you that there exists a fundamental rate-loss trade-off. That no protocol could ever exceed this purple line. Okay, and then this blue line is something that's achievable if you have perfect quantum computers and infinite energy. So that's maybe that would suggest that that's some kind of limit as well. And that was only known to be achievable at the time. And then we also depict what various more practical protocols are out there, what they can achieve. Okay, so after our work, in October 2015, there was a nice work of Stefano Pirandola and his colleagues that Stefano will talk about this afternoon. And using a different method, they established this upper bound. So what they did, in comparison, was to get rid of this eta in the numerator. And they used a different technique to do so. And I pressed the bad button. I didn't press any button. All right. Good, I'm glad it's back. All right, so they established this bound, and this is a significant improvement, and it corresponds to this blue line right here. Okay? And what they also showed by appealing to their earlier work is that if you have an infinite number of channel uses, infinite energy as well, and Alice and Bob have perfect quantum computers, so a very ideal scenario, then this is in fact achievable as well. Okay, so this is the capacity of the pure loss channel. This is the private capacity. The issues with it are the same as I mentioned before. It's a capacity asymptotic statement. And in the information theory literature, this kind of bound is called the weak converse bound. The particular method that was used there, it doesn't give any improved bounds for protocols using finite energy, but it should be mentioned that in many cases of interest, using these achievability methods, you can approach this closely with finite energy. And there was concurrent work of Kenneth Goodenough and collaborators that showed in some regimes that this finite energy squash entanglement can be tighter. So there's still more work to do. I mean, the ultimate capacity has been identified, and it's a very nice result, but there's still more to do. And the other thing is that there is this issue with unbounded shield systems that I mentioned was present in the squash entanglement work. You take a very careful look. So with many papers today, there's supplementary materials. So to figure out what's going on, you have to look in the supplementary material very carefully. In fact, this presentation will have supplementary material at the end for those who are super interested. Okay, so the similar issue with unbounded shield systems that are related to these private states of the Horodeskies. There's a similar issue, and this is something that we've addressed and fixed in this paper. Okay, so now I'm going to talk about the result that we have, the result with Mario and Marco. And this is an upper bound for non-asymptotic private capacity. Okay, so this is the bound that we find. We have a general approach that we call the meta-converse approach, and this is some language that has been used for some time in the classical information theory literature, and I'll talk about that more in depth later. But one consequence of this approach is this bound that applies to all n and all epsilon. Again, this is a bound for the unconstrained non-asymptotic private capacity, where you're allowed to use as much energy as you wish, but the bound does apply to all finite energy protocols as well. So what we have here, the first term is the term that Stefano and colleagues identified, and that is the capacity. And what we have is another term that's a function of epsilon, which is the infidelity of the key, the quality of the approximation, and this constant up top that depends on epsilon. This may look a little messy. I did think about this constant for a while. Other choices are possible, but eventually we just settled for this. Okay, so this is something that you can use if you're trying to build a quantum repeater and you're using a channel a finite number of times and hoping to have some infidelity epsilon. This is some bound that you can use to say that if your rate of secret key is exceeding this, then you have a quantum repeater. Okay, so this is what you can use to assess the performance of a quantum repeater. There are other variations of this bound that are possible. Maybe we don't know the loss parameter precisely. Maybe we know it's in some range, and so you can establish other variations of this bound as well. I won't get into that. Also, if eta is chosen adversarially in some way, then the smallest of the etas that are chosen adversarially is the bound. There are some remaining technical questions. Now we're getting to some really fine points, I guess. But I think that this C epsilon can be improved to this log 1 over 1 minus epsilon. So it is true if eta is 0. We can say that much. Because in that regime, the channel is entanglement breaking, and we know that the non-asymptotic private capacity of any entanglement breaking channel cannot exceed this divided by n. And so it's just something I think should be true. We're limited by the tools that we're using, tools from quantum hypothesis testing. But I think it would be nice, because then actually you'd have some very nice symmetry between this log 1 over 1 minus eta and log 1 over 1 minus epsilon. So it's kind of a very fine point. The other thing is that, is there any way to establish a bound that applies for protocols using finite energy? I think that would be interesting to develop. We are limited by the tools that we're using right now. Okay, so let me talk about this meta-converse approach. We are building on a vast literature that existed before us. I suppose to many of you, these just look like letters and numbers. Okay? But it's important to be there because people care about this stuff. Okay? So the meta-converse approach, we can, I suppose, go back to the 70s with work of Richard Blahout, famous information theorist, and he was the first to relate hypothesis testing to converses in information theory. So that idea goes back to the 70s, and then there was work of Yuri Polyansky, Vincent Poor, and Sergio Verdu in 2010, where they really developed this approach in great detail, and it was very influential in the classical information theory literature. And now there's been a sequence of papers in the quantum world that have used this approach, found classical capacities, quantum capacities. All right, this is the quantum capacity one. And so we're building on a very large literature. So I'll just sketch this, kind of the basic ideas behind it. There's a quantity called, now called hypothesis testing relative entropy. It behaves like a relative entropy, but it's useful for establishing finite size bounds. Protocols that are using a channel little n times, call it for approximation epsilon. What we do is to compare the state resulting, the actual state resulting from the protocol to a separable state. And in work of the Horodeskis in 2005 and 2009, that's Horodeskis and Oppenheim, they showed that separable states are useless for private communication. That has been kind of the guiding theme in these meta-converse approaches. For classical communication, you compare the actual state with the product state because product state corresponds to the channel replacing the input with some other state, and that is a channel that is useless for classical communication. In this work, I think this is with Marco and Andreas Winter, we compared the states, we were considering quantum communication, so we compared the output of the protocol with a positive partial transpose state, which was shown in various works to be useless for quantum communication, so we're kind of continuing that idea in this work. And what this does is this hypothesis testing relative entropy, manipulating it, we can extract the relevant parameters of the protocol, which include the number of channel uses, the rate, the log of the dimension of the key system divided by the number of channel uses, and the approximation parameter. We relate them via some information-like quantity. So it's some kind of one-shot entropy that we're using. And the reason it's called meta-converse is because it leads to various other converses. This is some terminology that was introduced in this Ansky-Poor-Verdu paper. So as a consequence, we get Renyi entropy strong converse bounds. And we also get bounds in terms of relative entropy and relative entropy variance. Those are some things that I'll define on the next slide, and might be the most technical. Is the mic not working? You can hear me? No. To be on? Hello? All right, we're back. Okay. Okay, so as a consequence, we get this statement that I'm going to get in trouble for. We get the tightest known upper bounds for non-asymptotic private capacity. 5 minutes. Okay, so I have 5 minutes. I think you want to see results, so I'm going to skip this. These are some technicalities. This is the hypothesis testing relative entropy that we're using. In our case, rho is the state that's output from the protocol. Sigma is a separable state. You do some manipulations, you get nice expansions. All right, apologies for that. Okay, so we get some nice bounds for channels of interest, at least in theory world. So the qubit dephasing channel is something that has popped up quite a bit. This is the channel where the input either gets through or it gets a phase flip with some probability. And gamma is the dephasing parameter. And what we find here is a nice expansion for this non-asymptotic private capacity. Here is what's called the first order term. This is the private capacity. This is something called the second order term. It represents the back off from capacity for finite n. If epsilon is less than a half, then this phi inverse is negative. So it represents the back off from capacity for regimes of interest. This phi inverse is the cumulative, phi is the cumulative standard Gaussian. And then we have a third order term, and then fourth order term, you can look at that as well. Okay, but we didn't do that. All right, so this is the kind of plot we can make, and this is really taken directly from work of Marco Tom-Michel, Mario Berta, and Joe Rennes, where they were considering quantum capacity, non-asymptotic quantum capacity. And it turns out for this channel, their non-asymptotic quantum and private capacities coincide. So here up top, we have the actual capacity. So to get that, you need to go to infinity, right? And what we can do with our techniques is to establish outer bounds. These outer bounds and inner bounds come from, via some translation to the quantum world, we can use some results that were known in classical information theory. So to get these exact bounds, you have to solve some equations, and so that's why you get some bumpiness due to discretization. And what's plotted in the middle is this third order approximation that's given right here. Okay, so you can see that it does a pretty good job of approximating. It gets better and better as n gets larger and larger. To make a reasonable plot for some finite number of channel uses, we took a bad key, right? So like this 5% is not a good key, but it's just something to illustrate the point. If epsilon is smaller, it's going to take longer to approach capacity. Okay, you'll need more channel uses. Oops. Okay, the other example that is strongly related to the photon loss channel is an eraser channel. Okay, And so if you're sending a single photon where information is encoded into polarization, if you're sending that through a loss channel, then the induced channel is an eraser channel. Okay, so this is relevant to the regime, to channels of interest. And for this channel, because it has a nice form, either the state gets through or some orthogonal state is output to Bob. It's easier to solve things for it. So the exact capacity is given as the solution to this equation. You can expand this and have something similar that we talked about in the previous slide. This is the capacity. This is the actual private capacity of the erasure channel. This is the back-off from capacity. There is no third order term, and then there's the fourth order term, which is, we just write as big O. And for this one, you can compute the exact boundary by solving that equation, okay? And the third order approximation does very well. Okay, so you said 5 minutes? Pretty good, all right. We have other results. These are bosonic channels of interest. These are the capacities that were identified by Stefano and colleagues. And then we identified something that we call unconstrained relative entropy variance of these channels. Okay, so these are thermal channels, amplifier channels, additive noise channels, and we can get strong converse bounds. Okay, so these are kind of similar to things I've been showing on other slides. So here's the capacities, the first order terms. Here's the back-off from capacity. For technical reasons, we don't know how to put the phi inverse epsilon there for these channels. I think it should be possible. This is the constant C of epsilon that I wrote before. Ideally, we want that to be log of 1 over 1 minus epsilon. All right, so I'm done. These are the things we did. We've done some follow-up works, and I'd also like to mention this work of Good Enough and collaborators, where they extended this squash entanglement technique to much more general situations. Thank you.
Are there any questions for Mark?
So first of all, Mark, congratulations for the talk. I mean, I like the talk about also the class, of course, that you got. I have a question regarding the problem with the shield system that you mentioned at the beginning. That is very one of the first slides. So can you elaborate more what the problem is in that case?
So in this work of the Horodetsky's, okay, so I actually have supplementary material. All right.
That's
20
nice.
slides of it? Okay, so.
That's why you have 40 slides.
Okay, so this is this notion that the Horodetsky's came up with. So they came up with this notion of what it means to have a quantum key, and they define it in this way. This is the ideal key that you'd like to have. The A and B systems are the key systems of Alice and Bob, and E is the environment system. So this state, you can purify it, okay? And you can assume that Alice and Bob have the purification, okay? So this is, or it's simply everything that Eve does not have, okay? And if you purify such a state, and then you trace over Eve, you get this kind of state. Okay, so this is what they called a bipartite private state. And in the key systems, you have these, this A and B is the key systems. You have a maximally entangled state. This unitary is what they called twisting. And that's there. It prevents Alice and Bob from actually getting a maximally entangled state in general, but it also prevents Eve from getting the key. In the case of protocols, these shield systems need not be bounded. And that's especially true for infinite dimensional bosonic channels. So that was some issue that we did not address in our first paper on squash entanglement. I will blame Matthias Christendal for not addressing this in his PhD thesis. It was subsequently addressed in papers of Matthias that I didn't do my job of reading the literature properly. And then later, this issue was identified and solved in the summer. And you know, it's a subtle issue, but it's there and it needs to be addressed. So that's...
All right. I think.
All right.
Thanks again to Mark.